basics of heat transfer, and we discuss the course contents, what are the program and class learning objectives, and then we discussed law of conservation of energy, okay, and what should be its form for a control volume and what should be its form for control surface. Okay, now we would move on and we see what are the basic mechanisms for heat transfer. Now there are those three basic mechanisms for heat transfer. Those mechanisms you already know. You might have seen it in your elementary physics course as well. Conduction, convection and radiation. Okay, I told you this conduction would happen in a single medium. When the molecules of a single medium, they collide with each other, they transfer their energy. Okay, so you can say that they transfer their energy in the kinetic form. Why? Because they vibrate. Okay, they vibrate, and if the molecules are closer enough, they would have strong conduction, just like in cases of solids. In case of liquids, molecules are not that densely packed. Okay, so that is why you can say conduction would be kind of at a lower rate in liquids, and in gases that would be kind of minimal. So these are few examples. I would explain each of these mechanisms one by one. This is the agenda for today's class. Let's talk about this one. You can see that this is a plane wall. By the way, this is a representation of a plane wall. Okay, this side is being kept at a temperature T1, this side is being kept at a temperature T2. You can say that T1 is greater than T2. Now the heat should flow from the higher temperature to the lower temperature, isn't it? So you can say that this is an arrow, which is basically this Q double bar that represents heat transfer rate. That represents heat transfer rate per unit area. Remember, this is something which is heat transfer rate per unit area. So you can see that this term generally would represent heat transfer rate per unit area. We will talk about that. If you just put a dot over there, that dot represents time derivative. That dot represents time derivative. Okay. Now this double dash, if you have a dash on some denotation of a physical quantity, that represents derivative with respect to spatial variable, let's say x, y or z. Okay, so I would explain it. Just hold on for a minute, and I would write down its complete relation and then show you why we have put this double dash over there. Anyways, so my point is that you can see that if this is the wall, just look at this point very carefully. If this is the wall, you can say that the wall is in the vertical direction. The heat is being transferred in its normal direction, right? So this is one example for conduction through a solid or a stationary fluid. Even if the fluid is stationary, I told you that if the fluid is stationary, within the fluid you would have what kind of heat transfer? Conduction. And if the fluid is interacting with some other medium, let's say some other liquid, some other solid, some other gas, just like air blowing on a surface of the sea, let's say water flowing in a pipe. So what kind of heat transfer would occur at the wall, or let's say at the interface between sea and the air? That would be convection. That would be what? Convection. Now similarly, in that case, generally you would see that this infinity sign represents free stream conditions. This infinity sign represents free stream condition. Just like if you have T infinity, it means this represents temperature for the free stream, undisturbed stream, which is there in the atmosphere. Okay, and then you may have taken like P infinity, where the pressure of atmospheric, rho infinity, V infinity. Okay, you might have seen those terms in fluid mechanics course as well. So if this surface, this solid surface, or let's say this is the sea surface, liquid surface, whatever it is, if this surface is at a temperature Ts and the moving fluid is having a temperature of T infinity, Ts is greater than T infinity, so heat should start flowing from this medium to this free stream medium, isn't it? So, and again, this direction of heat flow would be perpendicular to what? This area, this interacting area between the two media. Okay, so let's see the example of the radiation. If you have this kind of surface, obviously all the bodies, they emit certain radiations, they emit certain waves. Okay, so just like it does not require any kind of medium to pass on heat. You can see that the sunlight is a very general example, is a very good example for radiation. Okay, similarly, if there is a heater installed in this room, still at a distance you can feel that the heat is coming in, even if there is no air around you. Okay, human body, everybody emits radiation, everybody absorbs radiation. So these are two capabilities of each and every body. Okay, so let's talk about conduction in detail. This is kind of a formal definition. Conduction is the transfer of energy from the more energetic particles to the adjacent less energetic ones as a result of interaction between the particles. Just consider these are the few particles within certain media. Let's say these are the molecules. This is one side. Just consider it as a wall, for example. This is another side, T1, this temperature, T2, this temperature. So this is T1 and this side is at temperature T2. Now if T1 is greater than T2, you can see that the energy would be transferred from this side to this side. Okay, now if you can differentiate the colors for these high energy molecules and these low energy molecules, can you see that? Now you can see that these high energy molecules, they will collide with those low energy molecules and they transfer heat through that collision, right? So if you remember that in your chemistry course or in your physics course, elementary level, you might have heard about a theory which is kinetic theory of gases, and there you might have seen that temperature is a measure of what? Kinetic energy, isn't it? So temperature is also representing what? It's a measure of what would be the direction of heat flow, what would be the direction of the heat flow. So you can say that if these molecules are at a higher temperature, they would be having a higher kinetic energy, and certainly so those high energy molecules, they would simply transfer their energy to the low energy molecules, and that energy interaction would happen by which mechanism? The collision, right? They collide with each other, and obviously the collision would be more powerful if the molecules have smaller distances between them, right? The distance between the molecules is small. In case of gases, you have a higher distance, larger distances, so it means that conduction would be kind of minimal, in case of gases. So now I hope you understand this definition. Conduction is the transfer of energy from the more energetic particles to the adjacent less energetic ones as a result of interaction between the particles. Okay, you see, this is interaction between the particles. So what kind of interaction it is? Collision. Okay, then collision, the conduction takes place in solids, gases and liquids. It can only happen in one media. In gases or liquids, conduction is due to collision and diffusion of the molecules during their random motion. Now diffusion means traveling of the molecules. Traveling of the molecules from one point to the other. Let's say if I just spray a bottle at this point I spray a bottle. So after some time you would also be feeling that kind of smell, isn't it? You would be having that feeling that there is some smell within this room. So basically those molecules travel. In that case, that smell travels due to what? Diffusion. Okay, so molecules diffuse to the other directions, diffuse in the whole room, and you would see that there is some kind of smell. There has been some spray of the bottle at some point within this room. So this is something which is known as diffusion. Okay, so you can say in case of gases and liquids, conduction may happen due to diffusion as well. Why? Because not in solids. Diffusion does not occur in solids. Why? Because solid molecules, they are tightly packed. Their surrounding molecules, they would not allow the molecule to displace from its original place, isn't it? It would stay at its original place and keep vibrating. But in case of liquids and solids, they do what? They can travel. They can travel from one point to the other. Why? Because the intermolecular forces are kind of very small. Okay, so that is why you can say in gases or liquids, conduction is due to collision and diffusion of the molecules during their random motion. But in case of solids, it only occurs due to collision, right? And it all happens due to intermolecular forces. Intermolecular forces are the basic agency for these interactions. In solids, it is due to the combination of vibrations of the molecules in a lattice and energy transport by free electrons. Okay, so I hope it is quite clear. Now see, I would just talk about this plot because you would keep looking at this kind of plot throughout this course. Let's say this is temperature axis and this is basically representing x location. Now if this temperature is at T1 and this temperature is kind of at T2, for example this temperature is T2, so maybe the temperature variation is like this. So you can see that the heat flux would be from which side to which side? It would go from the upper surface to the lower surface. Okay, so we may speak of the net transfer of energy by random molecular motion as diffusion of energy. So this is not diffusion of molecules. You can say that the net transfer of energy is basically what? Diffusion of energy. It is not diffusion of molecule. Why diffusion of energy? Because energy is being transferred, not the molecules themselves in case of solids. But in case of liquids and gases, it's the energy diffusion along with molecular diffusion, right? So these are few salient features of this conduction. So the basic thing is, I told you that in engineering, what you need to do, you need to predict the things, isn't it? As engineers, you need to approximate the systems behavior. And how do you do it? You perform certain kind of experiments. Either you plot those empirical relations or do you derive mathematical equations, isn't it? You might have seen those empirical relations in your fluid mechanics course. You remember Buckingham Pi theorem and all that. So what you do is, you basically perform certain experiments and you try to predict that if these are the conditions and the system is behaving like this, if you slightly modify the conditions, where would it go? Okay, and that's why you always try to develop mathematical models. Why mathematical models? Because in that case you don't need to perform those experiments each and every time. It involves cost. Okay, so what you can see is you always try to develop the mathematical models, and sometimes those mathematical models, they are derived from the fundamental principles, just like law of conservation of energy, just like Newton's law. This is what? This is a fundamental principle. Fundamental principle means this holds every time in universe. Universal law. Just like sigma f equals ma, you can say that it would be kind of a universal law under certain dynamical conditions. If you talk about the law of conservation of mass or law of conservation of energy, these are the universal principles. Okay, you can't violate them. So these are fundamental laws. Sometimes your relations, your mathematical equations, they are derived through the fundamental relations, and sometimes those relations are not available to you. In that case, what you do? You perform experiments. When you perform experiments, you try to find out relation between different quantities. You say that these are basically, let's say, directly proportional terms, these are inversely proportional terms, and then you combine them and try to find out the constant of proportionality. You remember that process from your physics course or fluid mechanics course? So this is kind of experimental approach, or you can say that the empirical approach. But this empirical approach is very powerful. It is a very powerful technique because it basically, you can say, it unveils many physical quantities and their dependence on several parameters. Like for example, if I say that I want to find out the rate of heat conduction, and I say that its dependence is upon area, temperature difference and thickness of the wall. Let's say, just consider this is the wall. This one is the wall I am talking about. If this is the wall, its cross-sectional area, I am talking about this area. Its cross-sectional area is W cross H. You can say this is W and this is H. Now, if I say this is basically side view. If you look at this wall from this side, this is the side view. Okay. Now, if this is the side view, this side is at a temperature T1 and this side is at a temperature T2. You can say this side is at a temperature T2 and the side which is behind this one, this is at T1. Okay. So it is basically, again, in empirical approach, you need to be more intelligent. You can always say that this rate of heat conduction would be proportional to these parameters, for example. Okay, and someone says that these parameters include area, temperature difference and thickness. Thickness means what? This, right? This thickness of the wall. And temperature difference between this side and this side. Okay. Now see that whosoever performed that experiment, he determined that this Q dot is what? Rate of heat conduction, and for clarity I just put this conduction in the subscript. Q dot conduction is directly proportional to area. Which area? This cross sectional area, not the cross sectional area, by the way, this area. Okay, and this area is normal to the direction of the heat flow. This area is normal to the direction of heat flow. Then he determined that this Q conduction is also directly proportional to delta T, which is basically what? T1 minus T2. Similarly, he also determined that this Q dot conduction is inversely proportional to what? Thickness of the wall. Okay. Now, if I just combine all those things, I can say that Q dot conduction would be proportional to area into delta T divided by delta X. And if you want to convert this proportionality sign into equality, you would have what? a constant of proportionality which is K. This constant of proportionality is of physical significance, K A delta T by delta X, and this is known as thermal conductivity of the material of this wall. This K is known as what? Thermal conductivity of the material. Now this K represents how efficiently a material conducts heat. For example, for iron, if you have, let's say, a value of 60 units for K, and for water you have a value of, let's say, 0.6 units for K. So which one would be a better conductor? Iron. Iron would be a better conductor, right? Because it is having a greater amount of greater magnitude of thermal conductivity, so it transfers heat in an efficient way. So this law is known as Fourier law of heat conduction. This law is known as Fourier law of heat conduction, and whenever you try to model heat through conduction, you would use this relation. You would use this relation for conduction problems. Okay. Now let me write down this Fourier law of heat conduction in a more generic form. If you see in what kind of coordinate systems it has been written over there, it is partial by partial x. So this is a Cartesian coordinate system, x, y, z, right? So if you want to represent this Fourier law in the other coordinate systems, so obviously you need to have a more generic form. So in any case, if I say that this heat conduction is Q dot conduction is area, thermal conductivity, partial T by partial N. Just look at this, partial T by partial X. What is it? This is delta T. This is change in temperature with respect to what? Delta X. And delta X is what? This is something, this is the direction which is normal to this area, isn't it? This X is the direction which is normal to this area. So if you look at this one, what I am saying that this N is which direction? Normal to this area. So even if you have a curved surface, and you can see that what would be the direction of heat flux? Normal to this curved surface. Okay, normal to this curved surface. I hope from your calculus course, if you have the equation for this surface, you can always find out the normal to this surface. Okay. By the way, we will talk about that later on, no problem at all. This is just a generic form for partial T by partial N and Fourier law of heat conduction in any coordinate system. Right? Now, if I say that this is Q dot conduction over area equals K partial T by partial N, this N shows the direction only. Okay? So, if this is the area, so any quantity divided by its area would be what? Flux. You remember? Flux. So this is heat flux. This quantity, because we are talking about heat transfer, so this quantity divided by area is known as heat flux. Okay? So you can say that heat flux, which is the heat transfer rate per unit area, and area is which one? This is the normal area, normal to the direction of the flow. That would be equal to thermal conductivity multiplied by partial T by partial N. Okay? I hope you understand that. No problem at all. These are very simple things. By the way, this is not the most generic form of this relation. we would talk about another step as well, but after this few introductory stuff. Okay, so let's solve an example just to show you how to apply those kind of relations. The wall of an industrial furnace is constructed from 0.15 meter thick fire clay brick having a thermal conductivity of 1.7 watt per meter per Kelvin. If you have K, so K can be written as what? Q dot into delta X over A into delta T. So you can find out what are the units of K from this relation. It's very simple. Okay, so this is 1.7 watt per meter per Kelvin for this problem. Measurements made during steady state operation. Steady state means you are not involving any kind of time as far as the heat transfer rate is concerned. Okay, revealed temperatures of 1400 and 1150 Kelvin at the inner and the outer surfaces. So this is basically at 1400 Kelvin and this is at 1150 Kelvin. Respectively, what is the rate of heat loss through a wall that is 0.5 meter by 1.2 meter on a side? So dimensions are given to you. This is 1.2 meters and this is 0.5 meter. Okay, so now this is also given to you. Thickness delta X. Okay, so simply what you need to do is, it is asking for the rate of heat loss. It means it is asking for the rate of heat transfer. Heat loss for what? Loss would be from this side and gain would be for this side. So this is kind of heat transfer rate. Okay, so you can say that Q dot conduction would be, or Q dot loss would be Ka delta T by delta X. You know what is the value of K? You know what is area? Area would be this area. Why? Because heat is being transferred normal to this area, right? So delta T you already know, this is 1400 minus 1150, and then you have delta X equals the thickness of this wall, which is 0.15 meter. So you can see what is Q dot. Done? Okay. Now, this is quite interesting just to show you, because these kind of studies are also used to design the air conditioning system for a building. Air conditioning system. Why? Because you need to know what kind of heat is being generated within the room. That's how you can always design an air conditioning system for a building. Okay, and obviously you also need to take care of the cost as well. What cost it would take to extract heat from one system to the surroundings. So this is just another example. The roof of an electrically heated home is 6 meter long. You can see this is 6 meter, 8 meter wide, this is 8 meter and 0.25 meter thick. So this thickness is 0.25 meter and is made of a flat layer of concrete whose thermal conductivity is 0.8 watt per meter per degree centigrade. By the way, would there be any difference if you have per degree centigrade in the denominator or per unit Kelvin in the denominator for K? Just look at that. This is delta T. So delta T, the amount of delta T for degree centigrade or for degree Kelvin, that would remain the same. This is not T, this is delta T. You know that. If you convert the units, so that would remain the same. No problem at all. So a flat layer of concrete is there whose thermal conductivity is 0.8 watt per meter per degree centigrade. So what can you say about the magnitude? It is a very small magnitude. So it means thermal conductivity of the concrete would be very small. You need to put that kind of material on the roof which is having a very small thermal conductivity. That's why if you see that the roofs are made of tin or let's say iron or any other kind of metal, they get warmer very quickly. Okay, why? Because their thermal conductivity is large, right? So the temperatures of the inner and the outer surfaces of the roof one night are measured to be 15 degrees centigrade and 4 degrees centigrade. Let's say this inner side is having a temperature of 15 degrees centigrade, outside it is 4 degrees centigrade for a period of 10 hours. Okay, for 10 hours it has been measured. Now for 10 hours the temperature remains uniform. Remember that. This is how the statement is given to you. Determine the rate of heat loss through the roof that night. So if I say that find out the heat transfer rate, just forget about the time. If you say this is the heat transfer rate and then you let's say you find out this heat transfer rate. So by the way, what does this represent? Q dot. Isn't it? That's what it is. Heat transfer rate. This is what, and in more technical term this would be partial Q by partial T. So this is what this is. Heat transfer rate means heat transferred per unit time. Remember, this is a difference. We are talking about heat transferred per unit time. This is heat transfer rate. That's what it is. This relation tells you something about heat transfer rate. So if you know what is the heat transfer rate, it means you are talking about the amount of heat transferred in a unit time, and that unit time is what we are talking about, seconds. Okay, and you can always calculate the seconds for 10 hours and you can multiply this Q dot with those seconds having been converted from 10 hours. You can always find out how much heat has been transferred from one side to the other in 10 hours. Do you understand my point? So this is the point I want to show you, that this Q dot is giving you what kind of information? Heat transfer per unit time. Okay, so please take care of this fact, that don't forget that you are talking about steady state conditions, but what does that steady state condition mean? This is for Q dot. Q dot is not changing with respect to time. Q dot remains the same. Okay, and obviously the cost of that heat loss to the homeowner, if the cost of electricity is 0.08 per kilowatt hour, so you can always convert that amount of heat into watt hour, multiply it with seconds, or let's say convert it into hours. Okay, and then you can see if for 1 kilowatt hour this is the amount, you can always multiply the total kilowatt hour by that amount. Okay, this is how you can have your gas bills or electricity bills as well. This is how you do it, right? For 1 unit you say this is the price, how many for let's say 100 units. Okay, so few important properties for thermal conductivity. I told you what is the information given to you by thermal conductivity. That information is about the capability of the material to conduct heat. To conduct heat means to transfer the heat from one point to the other within a single medium. Okay, so different materials store heat differently, obviously, because their capability is different, and we have defined the property specific heat as a measure of material's ability to store thermal energy. I will talk about that point also, but just let me explain this one. The thermal conductivity is a measure of the material's ability to conduct heat. Cp is equal to 4.18 kilojoule per kg degree centigrade for water. Now Cp is what? This is the specific heat. You have seen that term in your thermodynamics course. This is specific heat. Now specific heat represents the capability of the material to store the heat. Now these are two different things. One property is giving you information about conductivity property, how better the material can conduct heat from one point to the other. The other property is giving you information on storage capability of the material, right? So few materials can be good at storing the heat and few materials can be good at conducting the heat. Okay, so there are two examples, water and iron. This Cp is 4.18 kilojoule per kg degree centigrade for water, and this is having a magnitude of 0.45 for iron, Cp. So which one is having a better capability to store heat? To store heat, that would be water. Why? Because it is having a greater amount of Cp. If you look at the thermal conductivity, for water it is 0.608 units. Those are the units. For iron, these are the units. Now which one is a better conductor? Iron is a better conductor. Okay. So before taking decision on the use of any material, if you want to transfer heat through that material, you need to look at all those properties. What is the value of Cp? What is the value of conductivity? You need to see all those things. Okay, that's how you decide what kind of material should be used in a particular application. Which material can retain the most energy for a greater time? Yes, that property would be thermal diffusivity. I would explain it in the next slide. That property is thermal diffusivity. Okay, so just hold on for a second. I have just told you the name, that there is some property which can be used for that purpose. So by the way, that property is kind of a relation between those two quantities, Cp and K. Okay, so I would explain it. So now you know that there are two kinds of material capabilities which we are discussing till this point. Heat storage and heat conductivity. Cp gives you a measure of heat storing capability. K gives you a measure of heat conductivity capability. Now water is a poor heat conductor relative to iron, although water is an excellent medium to store thermal energy. So, right? Similarly, thermal conductivity of a material can be defined as the rate of heat transfer through a unit thickness of the material per unit area per unit temperature difference. That's the same definition I wrote in the previous slide. K is what? Q dot delta X over K delta T. Okay, so this is something which is not K, this is A. Okay, A delta T. So you can say that rate of heat transfer through a unit thickness of the material per unit area per unit temperature difference. That's how you define it, right? Now this table shows different values for different materials of thermal conductivity. You see, for diamond you have 2300 units of K, much greater than any other material. Now this is urethane, rigid foam. You see, its K is almost equal to air. Now why do you put always, you might have seen those kind of roofs over there. Why have you put that kind of foam on the roof? It is a poor conductor of heat. This is not for the purpose of decoration only, right? It is there for what? Insulation. Okay, and you can see that this is the reason. it is having a thermal conductivity equal to air. It does not allow the heat to conduct from one side to the other. Okay. Similarly, you can say that, so if you want to have a better conductor, use diamond. But obviously there would be a cost involvement as well. So look at some other choices, right? This figure, it just represents an experimental equipment given in one of the books for the measurement of thermal conductivity. Like for example, how can you measure thermal conductivity of any material? Like if you install the heater in some equipment, this is insulated equipment, on three sides it has been insulated. If you install this heater, you keep it at a temperature T1, you know what is the heat transfer, heat generation capability of this heater, because heater generates heat, right? It would generate heat at a certain rate. So if you know, obviously every heater has its own specification, that some heaters they produce more heat, some heaters they produce less heat. So it depends on how efficiently it converts electrical energy into the heat energy. Okay, so this Q dot G, it can be known through the design specifications of the heater. T1 it can be known, T2 it also can be known. Now if you insulate all those three sides, it means the heat has only one direction to flow, in this direction, right? If you also do not put insulation on these two sides, heat would also start flowing from here to here. So to avoid that kind of heat transfer, you install insulation on those two top and bottom sides. You also install insulation on that side as well. So whatever the heat is being generated by the heater, that is being transferred to this side in this direction. So now if you know T1, you know T2, you know what is the thickness of this material, and you know Q dot G, can you find out K? Now K is something for this wall. This wall is made of the material we are talking about. Okay, this is just one example of a very simple example of how you can measure the conductivity. So there is a very important point behind this concept, that if you put insulation on three sides, you are only allowing the heat to transfer in this direction. And this is one example of 1D heat transfer phenomena. This is what you say that this is 1D. Why? Because you are putting insulation on the other sides. Okay, if you do not put insulation on the top and the bottom side, it would become 2D. Okay. So this figure is simply representing the range of values for K for different materials. You see on the y-axis you have K. The kinetic theory of gases predicts, and the experiments confirm, that the thermal conductivity of gases is proportional to the square root of the absolute temperature T. You remember where I started from this lecture? I started this lecture from this point. Kinetic theory of gases, where I was talking about the Coulombian. Okay, and inversely proportional to the square root of the molar mass. Chemistry, molar mass. You remember, if you represent the atomic or the molecular weight of any metal or any non-metal, any entity in grams, that is something which is what? Molar mass. Okay. So for gases, this kinetic theory of gases is only applicable for gases, right? So it says that thermal conductivity of gases is proportional to the square root of the absolute temperature T, and then it is inversely proportional to the square root of the molar mass. So through this table you can only see that gases are having the lowest values for K: hydrogen, helium, air, carbon dioxide and all that. and then you have insulators. It means the designed insulators, they are good conductors, better conductors as compared to the gases. So if you ideally, if you want to stop the heat from conduction, you should use what? Gases. Okay, but you can't do that. Obviously you can't do that. You need to keep the gas within a solid boundary as well. So you need to go for what? Foams or woods or fibers. Within that frame, foams are at the lowest side. You see this foam and air, I showed you the values as well. And then you have mercury, water and oils, oxides, rock, food, rubber, all that, and then you have metal alloys. And then at the very top you have quartz, which is one form of silicon, and then you have diamond graphite. You understand that? Now you remember this quartz or this silicon kind of materials, they are also used in electronic devices. So what is the purpose of having those materials in the electronic devices? What is the purpose with respect to the heat transfer? They are good conductors, and if you have installed a good mechanism to transfer heat from within the electronic device to the environment, you need to allow the heat to conduct and then to release it appropriately. Okay, so there are purposes. You don't use quartz because it transfers electricity, or let's say it's a good whatever, it's a good conductor. That's another aspect. So you can say that as a mechanical engineer you may be asked to design a heat transfer mechanism for any electronic device, right? So you need to look at all those properties. Which material should be used? Don't put foam over there. Okay, don't put foam over there. Why? Because if you put the foam over there, it would not allow the heat to get out of that medium, and obviously it would burn. Okay, then thermal conductivity of the gases is independent of the pressure in a wide range of pressure encountered in practice. It does not depend on pressure. It depends on temperature, it depends on molar mass. As far as the pressure is concerned, it remains the same. So unlike gases, the thermal conductivity of most liquids decrease with increasing temperature. Now if you increase the temperature, thermal conductivity of the liquid would decrease. Why is it so? Quite natural. If you increase the temperature, obviously the liquid would try to expand, right? If it tries to expand, it means the molecules, they would move towards a greater displacement from their surroundings. So their thermal conductivity would be kind of less if you increase the temperature. Question? Okay. So like gases, the conductivity of liquids decrease with increasing molar mass. These are something which have been measured through experiments. Okay, increased molar mass, you always say that this molar mass is what? You remember from chemistry, number of electrons or number of protons and neutrons. You remember that you can find in a certain atom. So those are representing the presence of the electrons as well. That molar mass kind of thing. This is the representing. That's how I see it. So liquid metals such as mercury and sodium have high thermal conductivities and very suitable for use in applications where high heat transfer rate to a liquid is desired, as in a nuclear power plant. So you use sodium and mercury, right? Have high thermal conductivities. If they have high thermal conductivities, it means they are good conductors. Okay. Similarly, unlike metals which are good electrical and heat conductors, crystalline solids such as diamond and semiconductors such as silicon are good heat conductors but poor electrical conductors. So if you want to have an electrical insulation but you want to have a good heat conductor, what is the choice? Silicon, quartz or diamond. You understand that? So that's how you look at the properties which are required for the designing of any engineering device. What are the requirements? You might have seen those circuits where they have that kind of insulator, that grey material. You remember? You might have seen it. So this is something which is there. By the way, this word, this technical word lattice, this refers to what? Crystals in your materials course, right? I would just keep reminding you what kind of term you have seen in which course. Okay. These are also few representations for solids, liquids and gases. Just this thing, the thermal conductivity of an alloy is usually much lower than the thermal conductivity of either material, a metal of which it is composed. This is very important. Please note it down. For an alloy, the thermal conductivity would be lower than the actual material through which it has been formed. So if you want to make an alloy, to increase the thermal conductivity, you should not do it. Okay, it would reduce the thermal conductivity. Why? Because thermal conductivity is based upon what? It is based upon the crystalline structure, the spaces between the molecules. So if you mix two materials, you are obviously disturbing its own structure. Okay, so this is the reason, you can say, behind this phenomena. So for example, if you say copper and nickel, they have 401 and 91 units for K at 300 Kelvin. Now you see, temperature is also there with the property. It means K is a property of temperature. K is a property of temperature. So whenever you use K, you need to look at the tables at the end of your books. At what temperature you need the value of K. Okay, how you see it, obviously we need to look at that in the problems. But if you make a combination of 55% of copper and 45% of nickel, where does their thermal conductivity go? 23. Okay, then if you have copper 401 and aluminium 237, this is just 52, right? So you can say, even if you have 90% copper and 10% aluminium, so that's why you might have seen that advertisement as well, 100% pure copper, isn't it? 100% pure copper, those wires, electrical wires, although they are not pure coppers, we know that, but still you can claim it. But even if you see that composition and someone says we have 90% copper over there, if not 100%, so still they have brought down the thermal conductivity to what level? You can see it. Okay, even if in case of nickel or let's say aluminium, most of the time they use silver, they mix silver with copper, I think. Okay, most of the time those industrial units, they do that. So you can say that how it can affect the thermal conductivity, and that would increase the line losses and all that. Okay, so let's talk about this material. I was talking about thermal diffusivity. The product of density and the specific heat at constant pressure is called heat capacity. If you say Cp and multiply it with rho, that is something which is known as heat capacity. Okay, now if you want to see that what is the comparative performance of a system when it comes to storing the heat and conducting the heat, how can you compare? How can you compare whether it is a better conductor or let's say a better it can be storing the heat in a better way? So what you can see is, you can always take the ratio K over rho Cp. Now ideally this K over rho Cp would give you a what? A comparison of heat conducting property of a material and heat storing property of a material. If this magnitude is higher, what does that mean? The material is a good conductor. If this alpha property, which is known as thermal diffusivity, this is basically known as thermal diffusivity. This alpha is what? Thermal diffusivity. So K over rho Cp with these units, meter square per second. Remember these units, meter square per second. If you have a greater value of alpha, it means the material is a good conductor. If you have a lower value of alpha, especially less than 1, it means the material is good for storing heat. Look at this one. Silver is having an amount of, let's say, 149 into 10 raised to power minus 6. And then you have 127 and then you have 113, and look at those values at the end, 0.14. If it is 0.14, what does that mean? It is a good, it is not a good conductor. It is a good material for storage. Okay, so this is very important to understand. The thermal conductivity represents how well a material conducts heat, and the heat capacity shows how much energy a material stores per unit volume. Cp, and it is being multiplied by rho. Rho is what? Mass per unit volume. So it is being multiplied by Cp. Okay, if I say mass is 1 unit, let's say, so this is heat storing capacity per unit volume. Okay, so remember these properties, don't mix them. Thermal conductivity, specific heat, heat capacity, and then you have thermal diffusivity. Okay, and remember what their physical significance is, because they would be used in designing materials. Okay, so these are the relations, these are the conclusions which we have already drawn. A small value of thermal diffusivity means that heat is mostly absorbed by the material and small amount of heat would be conducted further. Okay, by the way, this conduction part is over. If you have any question, you can ask. Okay, now this is introduction for convection. Quite interesting. This, you can see that. You see, you try to lower the temperature of different things by blowing over it, right? So just like the hot egg, if you put it in front of a fan, you see that this fan is forcing the air, remember, forcing the air to move over this hot egg, and this forced movement of the air would try to extract heat from this hot egg. Okay, as compared to this, there is another situation. You just put the hot egg over there on a surface, on a table, no problem at all. The heat would be transferred to the surrounding air on its own. So these are two different phenomena. Where would you have more heat transfer rate? In which situation? This one or this one? Forced convection would be having a higher heat transfer rate. This is known as natural convection, where you do not have any mechanism to force the fluid to flow. If you do not have any mechanism to forcefully move the flow, it would be known as natural convection. Just like if you go in, let's say, in the free stream, obviously not in the free stream, on the road, and there is no there is no fan or no air conditioner. So what kind of convection it is? Natural convection. Okay. So let's talk about this definition more formal. Convection is the mode of energy transfer between a solid surface and the adjacent liquid or gas that is in motion. By the way, between a solid surface, this can be also replaced with a liquid as well. Just like convection over what? Sea surface. On one side it is water and on the other side it is air. Okay. So this is the mode of energy transfer between a solid surface and the adjacent liquid or gas that is in motion. This is very important. I hope now you understand through the examples which I have already given to you. Adjacent, interacting surfaces. Okay. It involves the combined effect of conduction and fluid motion, advection. Now advection is something which happens due to motion. Advection of molecules means you are talking about something which happens due to motion. Okay. And conduction is within the medium. Within the medium. Okay. Just like, for example, if I say that this is a solid surface, just to explain this point, this is a solid surface, there would be a layer of liquid which is sticking with this layer. These are the molecules, liquid molecules which are sticking with this layer. Now what would be the velocity of these molecules? Obviously equal to the velocity of the solid. You remember the no slip condition? Yes. Right? So if there is no relative velocity between this molecule and this molecule, the heat would be transferred through conduction. The heat would be transferred through conduction only. But over this molecule, over this layer, molecules are moving. And as you go farther from this layer, velocity increases. And then a boundary layer develops. We will talk about those things in great detail, inshallah. Right? So this is something which is conduction and advection. That on this interface, heat is being transferred due to conduction, but over it, it is being transferred due to advection. Okay. The faster the fluid motion, the greater the convection heat transfer. You see what this fan is doing? It is increasing the air velocity. It is increasing the air velocity. In the absence of any bulk fluid motion means just like the motion of the air, just like motion of water. Bulk means a greater amount, a larger group of molecules. Heat transfer between a solid surface and adjacent fluid is by pure conduction. Just like if you put tea in a cup and there is no motion of the, let's say, liquid molecules, it is just there, it is placed on the table, and once you touch the cup of tea, you feel it's hot. How the heat has been transferred? There is no motion involved. It is what? It is pure conduction. And within the medium as well, it is pure conduction. Why? Because there is no motion. Okay. So these are the delicate differences between the conduction and the convection. Please remember these points, because these are very important points to understand what kind of heat transfer mode is involved in a certain phenomenon. Okay. Now this is the same figure as I have shown you earlier. This is a solid surface. You have free stream fluid over there. You have temperature Ts, and then you see this is the velocity distribution. You remember that from your fluid mechanics course, the formation of boundary layer. Right? This is the formation of boundary layer. At this point you have no slip condition. The velocity is 0. Why? Because the solid is stationary. And then you reach, as you go above the velocity boundary layer, you reach the free stream condition. Okay, the same is the case for temperature distribution as well. At this point, the fluid layer would have temperature equal to Ts, and as you move up, that temperature approaches what? T infinity. isn't it? So it means this is another kind of boundary layer which is known as thermal boundary layer. This is velocity boundary layer. This is thermal boundary layer. Okay, and that thermal boundary layer is being developed due to what? Temperature difference of this solid and the free stream. Velocity boundary layer develops due to what? Velocity difference between this solid and this free stream. Okay, now what are the relations between those boundary layers? You need to wait for few more weeks for the answer of this question. Okay, now see, this is what, have you seen those kind of printed circuit boards within your PC, computers, or let's say any electronic device? You might have seen it. If you put a fan over there, the heat exchanger, not the heat exchanger by the way, it is something which is you can say heat extraction mechanism or whatever. So this is basically what? This is increasing the velocity of the air around this printed board circuit, right? And in case of forced convection, you have a higher heat transfer rate. If your fan stops, heat transfer rate would be very low, and in that case your computer may burn down. Just like the case for your automobile as well. You might have seen the fan. If your fan stops, engine may seize, isn't it? Why? Because it would not be able to keep extracting the heat, and your engine would not be having that proper heat transfer from its inner surface, and then the heat may go up to a level where it can seize the engine. Okay, so heat transfer processes that involve change of phase of a fluid are also considered to be convection. Your question, boiling. You see, this is convection, and this is convection due to what? This is kind of a diffusion as well, right? In this case, water vapors are going into the air molecules. This is mass transfer. Okay, heat is being transferred like this, and in case of collection of those water vapors around let's say a metal pipe or something like that where the cold water is going through, these are water droplets. This is also a phase change, isn't it? You have seen this phenomena. So this is also considered in the convection. Okay, such as water vapors, bubbles during boiling, or the fall of liquid droplets during condensation. So condensation and boiling, they are also considered in the convection phenomena. This is how heat is transferred in this case, right? Anyways, all of these things would be discussed in detail once we start convection. Now look at this mathematical relation used for defining convection heat transfer rate. This is known as Newton's law of cooling. This is known as Newton's law of cooling. Now in convection, Q dot convection is equal to H AS Ts minus T infinity. Now remember, this is the surface area. And this is the surface area of what? This is the surface area which is interacting area for the solid and the liquid. If the liquid is flowing over the surface, this would be the surface area. Okay, and heat transfer would be normal to it, kind of normal to it, right? So H is the convection coefficient. This H is convection coefficient, convection heat transfer coefficient. This Ts is the surface temperature, and this T infinity is free stream temperature. And remember, this is the most important thing. This H, this has nothing to do with the fluid. It has nothing to do with the fluid. It is not a fluid property, it is a flow property. H is what? It is not a fluid property, it is a flow property. Just like, for example, if you put a fan over there, your H would increase for the same kind of air. But if you remove the fan, you don't put it on, the H of the flow would be decreasing even if you have the same air. Okay, so you can say that H is not the fluid property, it is what? It is a flow property. And most of the time when someone says that I am doing research on convection, most of the time they are dealing with the values of H. They are looking at how to determine the values of convection heat transfer coefficient for a certain phenomenon. Okay, so it is an experimentally determined parameter. You can't determine it through any fundamental principle. I have already told you what is the fundamental principle, whose value depends on all variables influencing convection, such as the surface geometry, the nature of fluid motion, the properties of the fluid, and the bulk fluid velocity. Just like, for example, if you try to dry your hand, when you put them under a dryer, you see in the washrooms you use those dryers after washing your hands. So if you keep the hand closer to the dryer, would you be increasing the heat transfer? I mean, would you be quickly dry your hands? Would you be able to do that? Not at all. You need to keep it at a certain distance. Otherwise, if you keep them closer to the dryer, it would not let the air pass through your hands, pass over your hands. Okay, you need to keep them at a certain distance so that it can quickly dry your hands. And obviously, you don't keep it at a larger distance as well. You need to keep it at a certain distance so that you allow the air to pass over that freely. Okay, so this is something which is you can say which is just an example of how H varies, convection heat transfer coefficient, and it happens in all the heat transfer cases wherever you see convection. Okay, so typical values of convection heat transfer coefficient. Free convection of gases, it has these values, this range of values, 2 to 25. Free convection of liquids, 10 to 1000. Forced convection of gases, you can see how much it has been improved. Forced convection of liquids, and then boiling and condensation. Generally for all time kind of gases. By the way, you don't use helium for the convection. Obviously you need air. Okay, so even if you use the helium, still it would be within this range, or let's say plus minus 1, 2, no problem at all. This is a generalized range. Now see, you need to see the application as well, where you can find out the liquid to be employed in a certain device, or where you can find out the gases. Like for example, to conduct the heat from an electronic device, you can't use liquid, isn't it? That put water on your PC. Don't do that. Okay, don't say that I am trying to increase the heat transfer rate. So you need to be intelligent, right? This is again one example. A 2 meter long, 0.3 centimeter diameter electrical wire extends across a room at 15 degrees centigrade. This is 15 degrees centigrade as shown in this figure. Heat is generated in the wire as a result of resistance heating. Obviously it is a resistor wire, so it would heat up. And the surface temperature of the wire is measured to be 152 degrees centigrade in steady operation. What do you mean by steady operation? Heat transfer rate does not change with respect to time. Okay, heat transfer rate. Also the voltage drop and the electrical current through the wire are measured to be 60 volt and 1.5 ampere respectively. So you know voltage, you know current. Disregarding any heat transfer rate by radiation, determine the convection heat transfer coefficient for heat transfer between the outer surface. Now you need to find out what? H. What is the governing equation for convection? Newton's law of cooling. So Q dot convection is equal to what? HAS Ts minus T infinity. So can you find out this surface area? This is the cylindrical area of the wire, isn't it? This is where air is interacting with this wire. The surrounding air is interacting with this wire on this cylindrical area. Now, do you know that Ts? This is the surface temperature. Do you know this T infinity? This is T infinity. Now you need to find out this. You need to know this one. Q dot convection. How can you find out that Q dot convection? By the way, what is the heat to be convected? The heat which is being generated by the resistance. You remember that surface energy balance? Just see, its outer area is just a surface. So whatever is being generated inside, not the surface, let's treat it as a control volume. This wire as a control volume. So whatever is being generated should be going out, and there is only one way to let it out. This is convection. So Q generated would be what? Isn't it? This is power. So what is Q dot generated? Isn't it equal to energy per unit time? Energy spent per unit time. So units are the same. So you can use this relation to find out this Q dot convection. Okay, and that's how you can find out H. Oh, this is very ideal case. This is just to give you an idea that you need to find out, let's say, heat which is being sent out through convection, and that is equal to energy generation in the medium. That is the point to select this example. Okay. So any other point? So I would stop at this point and we will discuss radiation in the next lecture.